Recording. Okay, I'm presenting conditional positional encodings for vision transformers. My motivation is because many of the projects that I've worked on, the trends have required positional information. Segmentation obviously does. You need to basically map a voxel to a segmented voxel, and they usually align. And in surface reconstruction, you have to map voxels to like mesh coordinates. So basically position's always been important. And neural networks have very tenuous and varied ability to handle position. And while transformers have been kind of a boon for natural language processing, they have been not quite as impressive in image processing, and I think a key component of that is their positional encoding. But there's many other factors. But today I'm focusing on the positional encoding. I basically think that the ideal network has to maximize something called Equivariance, which is basically like the activation maps change in an expected way when things are translated, scaled, or rotated, or resolution is increased or sequence length is lengthened. And so basically preserving this property of equivariance while minimizing the need for data augmentation is key, because like there's networks that aren't very good at this property, but they achieve these results by extended training with data augmentation, which is like wasteful and time consuming for both the computers and for people. And additionally, these networks should be lightweight and fast. So I'm exploring those ideas. So the conditional positional encoding paper basically explores translation equivariance as a property, and for transformers, whereas the original VIT doesn't have this property very well, and it shows in segmentation tasks specifically in many ways. They also work with a more advanced vision transformer than the original VIT, which if you look at the literature, there's like a significant evolution since the original transformer, and still even more significant in vision transformers as well. So the pyramid vision transformer basically mimics some of the architectural design of UNet without in a slightly different way. Instead of having like multiple layers to get lower dimensional features, they have like an image pyramid where they get global features from different resolution images. So the reason that I find this interesting is that like whenever you're training on UNet or MeshNet and segmentation, if you like our GPUs have limited footprint, and training is larger GPU requirements than inference. So if you want to train on a small subvolume or a subsection of a image, and then you want to test on it, do inference on the full volume, so you don't have to like piece it back together. You have the UNet and MeshNet are able to do that because they preserve translation invariance, and I guess what I'm calling resolution equivariance, but that might not be the best term for it. But transformers don't have this capacity, at least the VIT doesn't. So improving positional encoding will help with that. So basically, the thing that is wrong with the original positional encoding can be probably described in many ways, but I would say it's basically just too top down, and that it's like it's thinking like it's thinking that the human brain acts like a mathematician and acting in a top down fashion, which I don't think neural networks do, and I doubt the human brain does. So basically, it's providing some sort of encoding of the absolute coordinates, like the indexes of the voxels or the pixels in an image, in such a way that the neural networks should be able to interpret them in a useful fashion. But the problem is it just doesn't work very well in practice, and some I've already kind of discussed some of the things that doesn't work well. But if you have in sequence processing, it doesn't generalize to longer sequences. But I'm not really particularly interested in that at the moment. But I think the problem that I'm interested in is very similar. And I'm interested in being able to go from small resolutions, such as like a 64 by 64 by 64 subvolume, to like the full volume inference, which is it's not exactly a longer sequence. It's a bigger volume, but it's a similar problem. CNNs had some issues at one point where Uber was exploring some problem that needed to know exact position information, and convolutions, they can sometimes fail on absolute positions as well. And so Uber implemented this IJ coordinate channel, and it's as a positional encoding for CNNs, and they were able to get like better reconstructions using positional encodings in CNNs, and I think that's worth keeping in mind. I talk about that a little bit more later. So, so solutions to improving transformers would, I mean, debatably improving, would be removing positional encodings. Like, do we need them at all? The empirical results show that we need them, at least the way things are currently configured. And so removing them drops accuracy on ImageNet, for example. You can interpolate and sort of like infer what positional encodings would be at longer sequences, but in practice that always requires fine-tuning, and the neural networks aren't a magic black box. They don't perform necessarily as you'd want them to. So interpolation is kind of, it works a little bit. It like you can fine-tune, but fine-tuning is not really a good option in terms of the use cases that we're interested in, of being able to train on small subvolumes and test on large full volume. So so the best option is to create newer, better encodings, in my opinion. So basically, I read through the literature as much as I think was, I think I did pretty good due diligence on this, and historically there was some several different, there's an evolution of like relative positional encodings in 2018 from the absolute positional encodings earlier, but currently this paper uses basically a function f that's applied to the tokens that are produced from self-attention, and the positional encoding is learned. So basically this function doesn't have to be a convolution, but it is. They do ablation studies to show other functions don't work much better, if at all. And this way, and there's ways of also getting absolute position as well, as I'll talk about later. So basically the mechanism for this is to like, so the self-attention predicts these class tokens, and not class, the feature tokens and class tokens, and the feature tokens are taken, reshaped into the shape of the image, and then a convolution is applied as if it were an image, even though it's like a latent space, and then that is added on to the like a residual connection is basically it's just added on to the layer and passed into the next layer. And I talk about why that might work well towards the end of the presentation. So zero padding is important because like it's only the idea is that these convolutions are learning sort of like how a voxel or a pixel relates to its neighbors, which is enough information to get position probably, and but the question is how would you get absolute position? And they do an ablation study that seems to indicate that zero padding is significant for getting the absolute position of a particular voxel. So the CPVT, so this is basically the PVT model, which is that pyramid vision transformer down here that uses different resolution maps. It has been altered in order to replace the positional encoding with the PEG generator, which is basically the convolutional function that is used to create a positional encoding. And they have other variants that replace the class token as well. And the class token, I think, is a little bit poorly understood. So just to sort of drive the concept of equivariance home, I think that's kind of an interesting topic. So like if you're just doing classification on faces and you don't have like a very diverse data set, it's conceivable that you could classify a face that's been scrambled just as well as you can classify a face that preserves order in a way that we can understand. And if it does that, if the performance doesn't change, then basically that neural network would be considered permutation invariant. But that might be okay for very fast, very lightweight classification that doesn't require extreme accuracy, but and doesn't have a lot of potential classes to conflict with it. But for segmentation, where you need to basically know where like the outline of a face is or outline of a brain is, that's not sufficient. So basically you have to add positional encoding. And historically, that's been done by mapping the indexes to some sort of sine function with a frequency such as like the length of the sequence or something like this. I think that makes more sense in terms of language modeling because the sequences can be very long and repeat. So like you don't want it's sort of the long sequences start to be considered the same as short sequences with this type of coding. But and there's nothing good about this encoding in my opinion in terms of like in terms of being a realistic bias for vision, because like indexes are linearly incremented. They're not like some sort of weird shape like this, and the sequence length is basically defined as like having a beginning and an end. So that doesn't seem to make much sense to me. The relative position encoding in 2018, this is a snapshot from Shaw's paper in 2018. So basically, the idea is that it's good enough to have give the positional encoding some sort of information about its neighbors, and it doesn't necessarily have to know about where it exists in the sequence. And it does pretty reasonable on certain classification tasks, but not all. And so it's better than having no encoding. But on, I think ImageNet it was that it doesn't perform as well as the absolute encoding because ImageNet places classes in the center. And if there's multiple things in an image, then if you can't locate the center, then you're kind of ambiguously predicting what class might exist. So basically, I've gone into this. So the and this pretty much. So basically, here's an example of the activation maps that like on MNIST that would have a property of translation invariance or translation equivariance, which are similar concepts. Basically, if you move the MNIST digit, the activation maps move correspondingly. And how that's useful in terms of segmentation is that if you move the MRI, the segmentation map moves accordingly. And that makes segmentation particularly easy. So anything that doesn't have this property is almost useless for segmentation. So basically we get to the ablation studies, and they basically demonstrate that no positional encoding is bad, but it can still do okay on like ImageNet, but learnable and sine cosine do better. But these are all with this is the relative positional encodings from Shaw that I mentioned. They don't do as well as I was saying earlier, and the stipulation is that they can't locate the center of the image as well enough to do as well as something that has absolute position. Let's see. So another thing that they have one other variant of their in their contributions, which is this, that replacing the class token. So there's when you go through the self-attention layer and then you predict the feature tokens, you also have a class token that is thought to have some sort of like global awareness of what's going on in here, but it's kind of like just tacked on at the end. It sometimes is randomly initialized as it makes its way through the layers. The global average pooling is used in order to replace this class token and give some sort of aggregate awareness of what's going on within the image. And basically, like it aggregates over the patches and forms a vector based on that is averaged and the way that pooling is traditionally averaged, which is like over a patch, for example. And that provides enough aggregate awareness to replace this thing, and the performance is better, and the footprint is more lightweight. So I didn't think it was really worth going into a deep dive into DEIT, but basically what this paper is doing is it uses a teacher-student model in order to like distill information from an existing model that does well, and they're comparing that against the pyramid vision transformer with the conditioned positional encoding. So the nice thing about this CPVT, I think, and the main thing to take away from the slides is that no fine tuning when going from low resolution to high resolution is required for segmentation. And so basically, like, they increase the resolutions to higher percentages. The DIT model's performance drops off as the resolution increases, but the CPVT performance holds a little bit better. So they basically trained on 224 by 224 images and evaluated on different higher resolution images all the way up to 512 by 512. So basically, like, this is just to reiterate what global average pooling was if I didn't do a sufficient job of explaining it, but the paper doesn't really go into detail about what they're doing. I infer from the paper that they're doing the averaging to create this vector over the patches, because that would create like, that might create the same size class token as before. So the global average pooling, it doesn't provide a huge improvement, but it provides like a 1% improvement or a 1.5% improvement. But it's faster and lighter weight than the class token. So the CPVT, their model, for a given set number of parameters, does better than the traditional transformer. So this is a little bit interesting. This is actually this is a fun experiment to me. So like this kind of shows that how we think about how neural networks do what they do is a little bit like is probably wrong, at least if you're not deeply involved in the literature. Sometimes, like for example, like we want to think that our brains needs like position from like the right next to each other, like being able to determine where a pixel is in a sequence, or where a pixel is in relation to its neighbors, or where a pixel is in terms of distant neighbors or whatever. But like random initialization of the positional encoding and not learning and just doing a convolution with a random convolutional filter by itself will improve the performance. And I've done some personal experiments where like I've done I froze the encoder to have random initialization and like trained the downstream task MLP for classification on like MNIST, and you'll see that even with a random encoder, you can do better than random guessing on 10 classes with the fine-tuned MLP. So I think that you don't like this doesn't have to be the way positional encoding is implemented. It doesn't necessarily have to be anything like absolute encoding or like relative encoding. It could be some combination of like dilation, or it could be random, or it could be multiple things. Let's see. Oh yeah. So basically, they find that they don't have to add positional encoding to every layer, but there are layers at which it makes the most impact if you're only using a single layer of positional encoding. And like the -1 layer would be like doing positional encoding on the input. The 0th layer is like doing positional encoding of the output of self-attention. And that's what does best. For the later layers, it still does better than having none, but it's not as impactful as early on in the network. Yeah, so basically these are the traditional encodings. So learned encoding, 2D sine cosine, relative positional encodings, with basically the same size models, but they the CPVT with the same number of parameters but using PEG wins, and PEG plus a different encoding is even better. But if you use PEG at multiple layers, it does better than all of these things. Yeah, that's a different slide. So, basically, this is showing how if you apply the different positional encoding to DIT, how it performs at different resolutions. Also, worthy of note is how PEG is lightweight because it's basically just a 3x3 filter. But the number of positional params increases dramatically for the traditional encodings, but the performance is not increased in proportion to the number of parameters. My own work shows that the number of parameters is actually kind of a bad measure of a model size in terms of its performance, because while it might have a few parameters, there's broadcasting, so a lot of those parameters get copied, and so the GPU footprint's hard to tell from just this alone. But it seems like their PEG is doing better. I put this here just maybe if anybody has comments about any of the had interest in any of the types of hyperparameters they were using. I'm familiar with like basically the top half, but I'm not too familiar with random mix-up prob, cut mix prob, and erasing prob, but they're newer and they're not applied to the later forms. So, and also something that was interesting to me is that dropout wasn't used anymore, but stochastic depth seemed to have replaced it. So that's worth noting. I should probably know that, but I haven't really been keeping up too much. The Ablation study on ImageNet with 0 paddings. So this basically shows that absolute position can be learned from having zero paddings. Zero paddings alone improve the accuracy by 2%. And that gives the network some very distinct edge to start counting from, is the idea. So like wherever the zero is it forms a large distinct edge. So multi-level peg, as I said previously, is really important, but worth noting is that if you increase the peg after a certain number of layers, it seems like it doesn't matter that much because the accuracy doesn't change. So they're implementing the positional encoding on 0 to 5, which is kind of where it peaks out. And then if you have 11 layers with, or maybe 12, with this encoding, positional encoding, it doesn't improve over having it only at 5 layers. So that, I'm curious if maybe the network in general might improve, stop improving after having 5 layers, or if it's just the positional encoding. It doesn't. Their ablation study didn't convince me, but I am convinced that what they're saying is correct. But I would like some more experiments to be certain. So basically, the important thing to me from this table is its segmentation performance. Since they're not using dice score and they're not using data sets that I'm particularly familiar with, I had to look up whether or not these measures were high. Mean intersection over union sounds very similar in calculation to dice, but and on this data set, 0.42 would be considered respectable, and 0.50 would probably be considered state of the art. It gets better than the ResNets and the PVT without their positional encoding and global average pooling, but there's still probably room for improvement. And let's see. Oh yeah, so basically this just shows that you don't need a large convolution in order to do well. You don't need a complex function in order to do particularly well. You just need a fairly simple convolution in order to do well, as the function f that PEG uses. So I was happy to see that while their code on GitHub was not representative of their paper in their appendix publishes the code block for PEG, which is basically the main thing you need. So basically you have this positional encoding block they call PEG. They only apply it in this instance is the first layer, so probably the layer after self-attention has been performed. And then they define PEG, which is basically like just a convolution that's applied over the entire reshaped. It's reshaped somewhere up here, probably, but the reshaped output, and then it's added like all positional encodings are onto the feature tokens. So the positional encoding of the feature tokens is added to the feature tokens. And that's not all that unlike residual connections type of thing, but I find it to be not very interpretable without further investigation. Attention maps, so that's interesting. So the DIT without positional encodings has like very chaotic, I mean, I don't know if you'd call it chaotic, but it's not as ordered as DIT with positional encodings, I would say. And the CPVT has similar attention maps, but this is only at like the first head and second encoder block. And so it changes the deeper you go and depending on which head you're looking at. So basically, they're comparing CPVT and DIT, but at different heads and different encoder layers. So it looks like, I mean, assuming they didn't cherry pick this in extreme, that DIT has this sort of almost like identity matrix for its attention. But CPVT has more diffuse attention, which I don't know if, I mean, it's doing better, so I assume that's better. But without positional encodings, it's so diffuse that it's probably like not useful. So so this is basically like my thoughts, and so I kind of, in some ways, I think positional encoding is a little bit of a useful numerical hack in the way it's implemented as just an addition onto the features. I know that's like very established as and ResNets and stuff like this, but it's just not very interpretable, in my opinion. I mean, you can say that it's shifting the mean and stuff like this, in a way similar to a bias might, but and I think that's what it's doing. But I still think that there's like better ways to conceptualize and place positional encoding potentially. Uber did Uber using convolutions considered positional encoding for convolutions as an additional channel. I think that makes more sense. And the reason I think that makes more sense is, so like basically if you consider the pixel as the thing that's the set or the sequence that's being permuted, then the channel is almost like all the channels together is like an object. So if you think of like the whole set of channels as like one object describing everything you need to know about the pixel, then adding the positional encoding there, I think, is more interpretable, and there's precedent for it in this Uber paper. I think that so something they did is, like I mentioned earlier, is they added it and increased the positional awareness of convolutions. So so for the most part, that's basically it. Is that the positional encoding needs to provide absolute position, relative position, and potentially neighborhood position, which is sort of like a very slightly more informed variation of relative position. But it doesn't necessarily have to be some sort of top-down thing like the order of the index from 0 to infinity run through a sine wave or a sine function or anything like this. I think that there's probably tremendous room for improvement, both in NLPs and in image transformers, in order to improve all aspects of the architectures. But the positional encoding in particular is just easy low-hanging fruit type of thing to fix. And that's pretty much most of my observations about positional encoding. And I wanted to thank everyone, and hopefully I wasn't talking to the wind, because I didn't hear anybody ask any questions, but yeah.
Well, thanks, Will.
All right.
Is any overlap with the masking stuff that Joanne, you're working on with Alex?
I'm not sure. I think what this is doing, if I'm interpreting this correctly, I think they're learning the positional encodings using these convolution layers. I think this HERA model I was talking about was doing it not necessarily using convolutions. I think it was learning the positional encodings using the pre-training operation.
Yeah, I'm curious, both of you, what your thoughts are on using these kind of data-driven based positional encodings versus, I think in MRI, there's an inclination to try to use like Atlas-based positional encodings in some way, or some kind of predetermined regions that are
known. I think that probably what I imagine you'll see is that you could probably use many positional encodings even at the same time, depending on the architecture. But certain problems will probably ignore certain positional encodings that are not useful and needed. So lighter weight architectures on a specific problem will use fewer positional encodings, and you'll see different performance based on what you'll choose up front. And it's really hard to know up front what's going to work best.
Makes sense.
So the positional, okay, so you take the patches, you reshape them back into some semblance of the image shape, and then you convolve over that. So to get the positional encodings, right? The thing that sticks out to me is when you're convolving in that space, those patches, because I think there's a lot of overlap, you're essentially getting a smoothing effect. So you're convolving over that smoothing effect. And I wondered how that changes the positional encoding. And because it strikes me that, like, why do you actually need to do this on the patches and not the image itself?
I mean, I think that's a legitimate question. I think they show that you can do it at multiple places and it helps, but basically if you're only going to do it at one place, the first layer seems to be the most impactful. I think it's more interpretable to do it at the first layer, but it seems like as a unit, adding it at multiple layers makes sense. But you'll see patterns within many neural networks that the hyperparameters that they choose to use on later layers are not necessarily the same ones that they use in earlier layers when they start getting really down into the most optimal and lightweight version. So like dilation being a significant example of this, like you'll see fanned out dilations as layers increase. So I think it's just what is the most efficient thing over time, combating with interpretability.
So if you tried to implement this in the VAT that we threw at for the NERVS workshop?
No, I was going to talk about that offline, but yeah.
Oh, yeah, no problem.
Yeah.
So I know that was something we had talked about, was just that the positional encoding was so arbitrary, it probably contributed to issues.
Yeah. I mean, like, I think basically in general, that would be the first thing to change. But I think that VIT is very, very rudimentary in terms of its advancements. So I think that if you find a more advanced segmenter that's also a transformer and apply this, you'll do better. And I think like you could implement things like strided patching or dilated patching or various types of positional encoding and to improve the MRI type of performance. The funny thing to me is that the inductive biases seem to be kind of converging on similar things from different approaches in CNN versus transformer. So like CNN in my mind is sort of like a bottom-up propagation of receptive field, and transformer is like a top-down propagation of global receptive field. But more modern variations of transformers are restricting how global their attention is in order to improve their memory footprint while maintaining the same amount of performance. So you're kind of like, it seems like global receptive field sounds really awesome, and it probably has some very niche use cases, but there's like a Goldilocks zone between how fast you propagate receptive field and the information loss in the network and its need to have global receptive field and stuff like this. And so I think there's just like kind of a natural search towards where that Goldilocks zone is of hyperparameters across different architectures. So
yeah, and I imagine the sort of solutions you're going to see in we call quote unquote enterprise thing. They're going to be ensembles and like really exhaustively Frankenstein together hyperparameter, hyper optimized models, right? Where you're just
Right.
like exhaustively searching, and that's like this kind of what the field has been doing in the past, and that makes sense for this kind of thing as well.
Yeah. Yeah, I think it would be nice to see optimizations occur at the same time as interpretability. I don't know like what the best approach is to do that, but like I think there's ways to sort of preserve interpretability while implementing these optimizations, but I don't think that there's really a whole lot of pressure to keep interpretability as in the forefront as we would like. So
Any other questions? Or people want to try this out? If that's it then, well, thank you, Will. I think we can. I'll stop it.
all right. Well, thanks everybody for attending, and have a good day.
Yeah, thank you.